In this video, we'll describe the cause of magnetic fields. So far, we've only discussed that boromagnets make magnetic fields. And so we really only know that there's certain types of materials that cause these magnetic fields, which then in turn cause magnetic forces. But the question is, why do they do that? What's going on at a microscopic level? Fundamentally, what's the stuff that causes magnetic fields? How does it work? Well, our first journey in exploring this idea, or the answer to this, is to watch a couple videos that show you some phenomena that you know, some behavior that you've seen that will end up causing magnetic fields. Now, our first example is going to be a very simple setup. It's going to be a wire wrapped around a iron nail. And this nail has a little bit of tape to make sure that the wire stays on, and one end of the wire is hooked up to a battery and it's about to be connected on the other side. So really this is a looped wire with an iron core in the middle. Now one thing I want to note is with these videos, I choose them based on what you see, and I mute them so both I can talk over, but also sometimes because the audio in here, the descriptions by the people doing them, are either not using the right language or describing it incorrectly. So if you're watching this video on the link that I have in the slides, don't really pay attention to what they say, just look at what they do. So what we're about to do is connect up the other end of the wire to the battery. That'll allow current to flow through it. When you've done that, you can then use the nail to pick up paper clips. Now, before this happened, that nail did not attract the paper clips. The nail itself is not magnetic. What we've seen before already with nails is that if you place them near a magnet, they become magnets themselves. So what's going on is the wire, running current through this wire, acts like a bar magnet. And then this bar magnet, or effectively this bar magnet, is turning the nail into a magnet, which increases the strength of it. So this same effect could have been done by simply having a loop of wire, but it is a more dramatic effect when it's also combined with a material that turns into a magnet in the presence of a magnetic field. The second video I want to show you is going to show you that running current through wires can cause magnetic fields, and to show you a little bit about what those magnetic fields look like. Here what we're going to do is see these these currents push on iron filings, which act like little compasses in that they'll turn in the direction of the magnetic field. And you'll be able to see the direction of the magnetic field lines by looking at the way in which these iron filings will organize themselves in the presence of a magnetic field. There are three different setups we'll look at. One is for a loop of wire. The second one has a larger loop of wire. The purpose of this setup is to put the segments of the wire that turn around far away from the iron filings. So only this is actually a rectangular piece, only the side of the rectangle that goes through the middle is actually close enough to the iron filings to affect them. So we'll show you what happens just due to that segment, which will act like a long straight wire. So this is a loop, this will act just like the long straight wire, and this is what happens if you loop together several in something that is very similar to something we'll call a solenoid later on. Now, the iron filings are these kind of gray mist that surrounds it. And it's hooked up so that a large current will run through these wires. Now, the fact that there are several wires rather than one wire only increases the size of this effect, but creates the same type of an effect if you only had a single. Now, the current is actually fairly large, on the order of an amp, which means that the wire will heat up fairly hot if left continuously running. So what they're going to do is let the current run for a short time, and then let it cool for a bit, and then press it again so you can see what happens. So what we'll see is a motion in these iron filings, and that'll indicate when the current begins to run. There, that's it, if you saw it. Here, on letting it cool, you can tell that that the iron filings were drawn in towards the loop, indicating there's an attraction. And there's a stronger effect nearer the wire than it is farther away, so the magnetic field is getting weaker the farther out. The other thing to note is that these seem to be forming loops, if you can tell, that they all turn in a sort of circular pattern around it. And this is something we'll want to keep in mind, that the magnetic field lines, which will be indicated by the direction of the iron filings, loop around the wire. Now, note that this segment of the wire is not really having any effect. It's hard to see from this angle, but it's actually several centimeters away from the actual iron filings. There's just no real depth perception from this camera view. And you can see that in the fact that there's a strong effect over here where the wire approaches close to the iron filings, but none along here because it's far away. The second case we'll look at is for this loop, and the smaller loop is close enough that all of the parts of the loop actually contribute to pushing on the filings. That these wires are close enough to actually have an effect due to the whole loop, not just the closest parts. And what you'll see is again that these also will move in response once we turn on the current, indicating that there's a magnetic field that's actually being produced. And the pattern looks somewhat similar nearby where it passes through, but in the middle you'll notice that they combine together to form a kind of interesting pattern. There it is. So here you can see quite clearly that the magnetic field lines come through the center, and it's a little stronger near the edges, but roughly constant in the middle, and that they have these, and if you actually continue on the outside, they tend to loop around. Right on this side, the filings aren't being pushed hard enough to show you the direction of the magnetic field, but they loop around the wires, coming in the middle and out the edges. Let's turn our attention to the third case. The third case, what we have is several of these loops put together. Again, these are close enough that the entire loop's affected, and this is going to mimic the magnetic field of something called a solenoid. Oh, and they just did it. I'll go flip back in case you missed it. Here's no current. Watch the directions of the filings in the middle. What you'll see is they'll abruptly turn all at one moment. I'll call it out when it occurs. There, just happened. And you can see that all the lines tend to run horizontal in this case, the way in which these iron filings go. And they can kind of tell also they curl out on the outside here. So again, you have an effect that looks kind of like this, where it loops around, but in the middle, they all tend to run in the same direction, in the left-right direction. So what's the take-home on this message? Well, the take-home is that in all of these cases, it was something we were familiar with already causing this magnetic field. It was current. In other words, it was moving charge. And perhaps this shouldn't surprise us. Take the case of looking at electric. We'll compare electric to magnetic forces. Well, electric forces are created by charge, and they're also felt by charge. It's the same type of stuff. We already showed that moving charge is what was required to feel a magnetic force. Remember that QVB sine theta. Or in terms of the language of current, a current was required, and that was ILB sine theta. So it's not perhaps surprising that the same stuff causes it, like in the electric case. It's also moving charge, or in other words, current, that creates a magnetic force. Now it's interesting here that both of these are related to charge, but do note that magnetic forces are caused by something slightly different than electric. They do have to be moving in order to feel or create a magnetic force. Stationary charge neither feels nor creates a magnetic force.